Well, hi everyone. Amir here from Sensor. I'm the co-founder and chief product. I'm very happy to be part of this session in Conf42 DevOps 2025. The name of this session is Kubernetes. Mine is the blind spots. We're going to focus around how to solve Kubernetes observability challenges and how that becomes a little bit easier when you can incorporate real-time topology. So what are we going to cover today? First of all of you, most of you are Kubernetes users. So, it's great, but it's also very hard to troubleshoot. We will delve into why it's hard to troubleshoot when we go a little further. We were going to connect it with the challenges of traditional observability toolkit, meaning if you have the classical logs, matrix, whatever, why that coming alone is not enough in modern dynamic environments. We're going to cover the concept of real-time topology, how it differs from dependency mapping, what to do, why, and how to implement it in real life. We'll give a few real-world use cases and try to tie in the concept of topology into one of your tools into one of the tools in your toolkit with regards to the troubleshooting process. We will see why eBPF is a very important enabler with regards to that, why the use of eBPF tools, eBPF open sources can yield very high benefits to enable the implementation of real-time topologies, and eventually a few tips of how to get started, whether it will be with a commercial tool or with an open source tool. So as we know, Kubernetes is great. We use it. We understand what we use it. Sometimes we don't understand what we use it, but it brings a lot of interesting challenges with regards to troubleshooting. There's a few reasons to that. First and foremost, the distributed nature. Like, there's no need to explain, but when we used and implemented monoliths, they had a lot of problems from operational perspective. They had a lot of problems from managing these big pieces of code. But from other aspect, they were closed, but they were easier to debug. With the distributed nature of Kubernetes, a lot of things happen. But first of all, we have a lot of more moving parts. And two, Kubernetes is very uniquely situated because it's a software layer, but it's a kind of a software infrastructure layer. In reality, when there's an issue in a Kubernetes-based deployment, it takes time and it's not that easy to understand whether it is an application issue or a Kubernetes issue, meaning how do you differentiate this the blurred line between application and infrastructure issue? The second one would be the dynamics, the ephemeral environments or the ephemeral nature of Kubernetes environment, which pods are coming up, pods are coming up, pods are going down. CI/CD pipelines are causing configuration changes, are causing code changes. It's of course not that easy to track that, it's also adding more complexity when we're trying to cope with troubleshooting. Complex networking. A lot of the things that Kubernetes does is to create abstraction upon abstractions upon abstractions. You can deploy two pods on the same server. You can deploy two pods in adjacent servers, but Kubernetes will try its best to make it seem like they're all one part of the same application. And that in real life can create a lot of troubleshooting cumbersomes. So elements like core DNS or proxies or the CNI plugin, which eventually create a flat networking model between them, are also adding to the troubleshooting complexity. Eventually, it's not that easy to sniff the network or look at each and every packet and understand what is going on just by means of the sheer abstraction layer that Kubernetes is imposing into the deployment. Shared resources and noisy neighbors. Of course, if we were in a world in which I have complete control over the infrastructure, meaning that when I'm looking at a pod or I'm looking at an application part, I don't need to account for what the infrastructure is doing, whether the infrastructure directly or because of another deployment, which is situated on the same node and by itself can cause metrics and cause other telemetry to be very noisy. So all of that is adding to the aggregate complexity, if you will. Black box or black boxes. meaning things that I don't really control. This could be infrastructure pieces, uh, pods which are third parties which I'm using, or containers which are third parties, and automation complexity. By itself, we touched it. We had a lot of other sessions in the past about how CI/CD pipeline by itself is essentially a noise generator when coming to troubleshooting. The effect that I'm trying not only to troubleshoot or trying to shoot at the target, but that target is all the while also moving. So I think in very high terms, that should give you a glance about the different elements which are the cause of complexity with regard to troubleshooting. We gave an example of logs on the right-hand side. I think logs are a very good example when speaking about distributed environments, because you're looking at a single point in time in a single element. And I always say it, the problem with logs is that they require more logs and rarely on the same place. The challenges with the observability toolkits as they exist today. So a lot of these observability toolkits were actually born, raised, nurtured for the world of monoliths. So a lot of things that started there, like Matrix and Log and Traces, are really coming from a world in which you should have a complete view over your application or your environment. And as we touched on before, that is something which is massively changing when looking at distributed environment. Metrics, everybody knows the concept, but we're looking at some sort of a quantity or a number. Usually it's there to track some sort of a performance telemetry aspect. So they allow you to track trends or to see absolute values, but eventually they're just numbers. You have nothing to do with them if you don't have some higher context to what they mean in the current time or in the current situation. For example, what's causing this spike in the CPU usage? There's a lot of other questions that you need to answer that will help you understand whether the spike in the CPU usage is something worrisome or just normal behavior of the application. Logs, so they're very coarse. They can provide you some granular detail about an issue, but they're fragmented. You see bits and pieces of logs from various elements in the system, and there's no one else other than an engineer that can tie it together, whether log A on point A and log B on point B has anything to do with one another, or generally are they correlated to the same issue. For example, I have a pod, I have an issue in a pod. What would that mean on a downstream element? For sure, we'll see logs there, but how do I do the logical connection between them? It's an interesting question. A good example would be losing a connection to a database from a client pod and then seeing a log on the database pod. There is a connection to be made there. Traces, which is oftenly used to go over a lot of these type of challenges. So they show service interaction. The real question is, how do you put them in place? And what is the effort to put them in place? Meaning essentially instrumenting the environment. It could be easy for some element which already supports it, but for legacy code or for other types of code bases, it could be a challenge by itself. eBPF, of course, is a technology that could help a lot with that. But achieving really traceable code on a high scale environment is not that easy. Very similar to getting coverage on code. So essentially, what we see in a lot of environments, they want to instrument the environment, but the gap to get the environment fully instrumented is very, very large. Moving forward, let's speak about the concept of real-time topology. I think just for a basic understanding, all of us always has some sort of a chart. It could be something that we drew. It could be an architecture slide or architecture chart of the environment. And the reason behind that is to give us the overall context, right? There's a lot of moving part, but if I want to capture in a glance what the system is doing, how it's built in high level terms. So for all of us, the concept of using a chart is very, very natural. Another concept which was evolved throughout the years is the concept of dependency map. Maybe I can create some sort of a static chart, but dynamically generated chart, updated updated in some sort of a low time interval, and create some sort of a view which mimics what the environment looks like, at least in the last couple of minutes or in the last couple of hours. Real-time topology, as we'll touch it, is like the evolvement on that into something which is fully dynamic. Real-time topology in that aspect should provide us the context required to eliminate blind spots. I want to generate more bits and pieces of context and help me understand how the metrical part, traces parts, logs part are really connected in real life and what should come into my mind. And with that, real-time topology is one of the most important tools. What is it? If we'll try to summarize it, it's live map of system relationship. In the Kubernetes case, it will be encompassing all the cluster layers and namespaces layer, going to the more granular elements like pods and services from the software perspective. Most of the time, if it's complex enough and smart enough real-time topology, it will incorporate the infrastructure element. It could go even much higher and show the interactions, but not only the interaction as a line from here to there, but also really these are the type of API, the type of information, the type of transactions that are traversing between the elements. Why should it matter? Why should it matter to us? The ability to do this logical connection, of course, gives us an element that we would have been doing in the troubleshooting process anyway. If I have an issue, let's say an API which now returns an error, what I would do as an engineer is start and backtrace that and try to follow a logical line. My API is bringing an error to the user, so it's probably experiencing some sort of an issue by itself. What would be the cause of that issue? Let's look at the log. Let's look at the metric. If I understand that, let's backtrace one step before that. Could it be that something like a database transaction couldn't be completed, or I couldn't read the value, and so on and so forth? And we're starting to essentially build a path on a graph or a path on topology. So the concept should be clear, because essentially we're mimicking the natural way of thinking for engineers, which is the backtracing. So that allows us to connect individual points into some sort of a more full view. How does it work? So essentially we're continuously updating the real-time topology to reflect the real-time changes, new services, new deployments, new interactions. And that allows us to grasp this massive amount of data in a way which is easy to present. Let's give an example. What we see in the following example is the real-time topology, in this case generated by eBPF, which allows us to track both external services, something which is not part of our deployment, but also deep dive into the structure of Kubernetes, looking at namespaces, looking at the deployments and the pods, and even the interaction between them to the protocol or API level. So for sure, if later we'll discuss it, if something happened here, or we have a metrical evidence, log evidence, trace evidence, being able to project that on the topology could explain a lot of things, or as part of the elimination process in troubleshooting, allows us to focus on the right things. Let's give an example. Let's think about a Kubernetes pod which is failing on readiness. Could happen because a lot of reasons. And let's say it's failing due to I/O. It's failing due to storage. It could be a local storage. It could be, by the way, an external storage. Database in that aspect is a storage. Any sort of an external repository would be a storage in that case. Being able to see that on a graph, being able to connect the dots, understanding that there is a correlation between how this pod readiness, in this case, pros is behaving with regards to an element is connected to, it's much easier to deduct when you have a real-time map. I'm connected to this database, this storage element, so on and so forth. Logical for me to look at that. So with regards to that, mapping the real topology or mapping the pod dependencies allows us to start and shrink the amount of element that we're looking at. And in that case, it allows us to understand that we need to focus on certain aspects. For in this example, the disk IO, which is really really the root cause, and then eventually decide what to do. Either adjust the probe configuration or change other configuration, enable different storage or other storage configuration. Another example, which a lot of time or a lot of you have faced in the past, is throttling, especially throttling when there is changes in the dynamics of the deployment, going up or down. For example, in this case, the scenario, we're speaking about an application which is under high traffic. This usually in a lot of deployment, there will be a connection between the amount of traffic to the size of the deployment through a load balancer, through whatever other means. But essentially what we're looking at here is the triggering of an HPA, of pod auto scaling. But eventually, a lot of the time, the deployment will scale. It doesn't mean that the infrastructure scale at the same pace or is well enough ready in order to absorb this scaling. And a lot of time in this situation, we see things like throttling. The number of pods has changed, but eventually we're looking at throttling from the infrastructure perspective. And even though we scaled, we get into a scenario in which we get malfunctions, or we're getting into the specific pods not being able to handle the load. How real-time topology will help here? So of course, one, being able to visually see that, being able to see the different interaction, visualizing the resource allocation. Are there more nodes or nodes group being allocated as part of the pod scaling? And that would enable teams, together with the other observability telemetry data, to either adjust the resources or limit the bandwidth, or to do whatever it takes in order to solve it. But just the ability to understand that this is an infrastructure issue, this is not an application issue, is of course already at least 50% steps towards the solution. Configured network policies, something that we've all seen and suffered from. I think it's a very easy case to understand how topology can help, because the fact that real-time topology is in many aspects very similar to a network topology map. So I think it's an easy aspect to understand. And other aspects, like we spoke about before, which are real-time topology. Topology is not only logical connectivity, also be infrastructure connectivity or whatever connectivity. But I think this one is very easy to comprehend. So for example, we have a pod or a microservice deployed, and it failed to communicate with another service, and it doesn't even have to happen. It could happen sporadically, could happen because of the configuration change. In real life, the complexities of getting into this scenario could be almost infinite. That's happening because of a network policy. It would be very hard without real-time topology to either comprehend that is the issue, or more than that, understand which adjacent services I should look at. It could be also very hard to debug only with something like logs, right? There's a lot of sessions going on. It could be any single session which is failing, which will give us an issue here. So really the lack of detailed logs or visibility or traces, if that specific path is not instrumented in the deployment, it's a very hard scenario to diagnose. But the ability here to have the service to service mapping, looking at the APIs, maybe on the topology itself, mark when there's an issue in one of these paths, be another great idea to do that. But the ability to show that, or even understand it might be here because I see logical connectivity, or I thought there should be a logical connectivity, but there is none, meaning that this could be really a network policy issue. It's a great example for the use of that, and the amount of automation that you can put around it can expose a lot of these cases. So what enables real-time topology? Essentially, there's ways to implement it. Could be done with things like distributed traces. If the environment is instrumented, that essentially following the distributed traces path could be a tool to create real-time topology. The one we're focusing on here is, of course, the use of eBPF. And with the use of eBPF, the ability to dynamically create a real-time topology. I think today most of you already understand it. It's a piece of technology, a part natively supported by the Linux kernel, extended Berkeley packet filtering, Essentially, the way to think about it is a small type of VM or feature within the kernel that allow us to run or safely run low-level instrumentation code, bits, or pieces of code, which from one hand are instrumented in the kernel, on the other hand will bring data to user space, kind of benefiting for both of the world. Main uses, so of course, traffic analysis, that was the original use for eBPF, the ability to trace network requests, messages, packets, sniff them. Of course, the most classical use. The importance for topology is the ability to track APIs and the ability to track essentially any kind of session. Infrastructure, app, and performance monitoring. So it's not only the ability to hook into the networking stack, but also the ability to hook into kernel calls or to hook into application calls. These are very important because it allows eDPF to create a more granular level of instrumentation. What kernel calls are being called could be important for a lot of use cases. What application calls are being issued by the application could be important for things like opening encrypted streams in HTTP. It could be the use of open sources and tracing. That's essentially how to auto-instrument pieces of code. If I can find in memory those function calls, of course I can add the trace point and enable that instrumentation. And all of these things, which are very relevant to observability, are naturally very, very important for security with a change of use case. Networking through enforced network policies and infrastructure and app call to protect or detect misbehavior with regards to things like open source usage or kernel usage, resource usage. So a lot of similar aspect, but the use cases on top are very much different. So why does it matter? eBPF, of course, enable deep observability. It's also native in Linux. In my perspective, that's maybe one of the most important things. It's like the native tool being put there in order for people implementing this type of mechanism. It's invaluable for complex distributed environments, both from security and observability perspective. So why is eBPF ideal for distributed systems? There's a lot of building blocks to that, and put a little bit of a caveat here. It's also very, very dependent on the implementation itself. But on the forefront, if you're doing it right, the ability to implement low latency monitoring, small pieces of eBPF code, bringing the relevant data, capturing the right element from the network packets can allow us to discover the environment and understand the connectivity without creating latency overhead or without creating other aspects which will implement the overall performance of the application. Enhanced visibility. So the ability to go and discover or to go and instrument specific elements which are important for us. It could be distributed queues. It could be database transaction. It could be whatever is important enough for us to deep dive into, and we don't have necessarily an alternative to monitor it at the fine granular level. Improved efficiency. So as a building block, security, observability, what have you, it can reduce the need for other or specific diagnostic tools. So being able to use eBPF as a building block to build the rest of the chain makes a lot of sense. We already see it, by the way, not only from observability perspective, but eBPF is being used on the platform to implement many things. So it could be load balancers, it could be service meshes, the observability tools, security tools, and the scalability. This being a very native Linux supported technology, being basically automatically enabled on each and every node is super important. Maybe on a different aspect, the ability to implement it not only for physical node, but for example, implement it for other ephemeral technologies with sidekicks or things like that can allow us to create a more consistent observability approach. Auto discovery. So in auto discovery, we're going one layer above it. It's not only, I will call it the data, but it's how we connect this data to a data model. something which takes it one layer above it and could allow us to start and speak about things like hierarchies or structure or create a more formal way of defining that. That would be the first aspect. And of course, with that, things like the use of machine learning or the use of pattern matching in order to take the data from Kubernetes, in order to take the data that we get from eBPF and match them or mesh them together to create not only a dynamic graph, but to put this data modeling on top of it and essentially creating something which is repeatable. This is a pod. This is a new pod or a new service. We have a node group, or we have identified a part of our application, which is a database or a business logic. And then again and again and again, even when data changes, still have it in the same format without essentially requiring any manual updates. Common pitfalls. Even though the concept is relatively simple, it has a lot of ways to get in the wrong direction. One, incomplete instrumentation. Eventually, we're trying to create a graph, or we're trying to create or look at a chart. The chart will be as good as the data which is there creating the chart. So missing critical data like logs or API or events or any other data eventually will create a non-complete view and it will not be used. So it's important not only to think about what data should go into there. Of course, eBPF can help with that, but also to have in mind what is the most important parts to have there to begin with. Stale topology maps. I think in many aspects, dependency maps are maybe suffering from that exact problem. Kubernetes environment or any distributed environments are constantly changing. If the topology updates are not automatic, and sure, if you're not being updated in a quick enough cadence, then the risk is of course taking a decision today on yesterday's data. Assuming that topology can solve everything, I think the most trivial one, but topology it's very powerful for troubleshooting, but it's rarely a smoking gun. Meaning what it gives you is it gives you the more context that you need in order to go in the direction of the root cause. But by itself is not a root cause. It's just a way to formalize or to model the observability data. Above that, or a layer above that, that's the entirety of the concept of AIOps. Assuming that I have that, and assuming I can extract this context, can I now go and automate the root cause process, or go at least into a process which allows me to lower the amount of alerts that I have and go in the direction of the solution. Tips for getting started. Assuming you want to do it by yourself or with a combination of open source tools or with commercial tools which allow. Remember the metadata. You can create or help yourself and choose a strategy with regards to creating the dynamic topology, but the Kubernetes metadata, it's eventually the tags, things like labels or names or config maps or event in Kubernetes. If you're putting them on the real-time topology, that's eventually how you populate that with the most important context. Yeah, I have the structure. Now I also have everything on top. Automate the topology map. So when you're looking and scrubbing for solutions, the dynamically update topology, think about these elements. How fast are they updating? Do they take into the consideration of the Kubernetes data, the infrastructure data, how fast they are to respond to frequent state changes? And eventually avoid context-binary pitfalls. Environments are large, environments are complex. It might be beneficial not to try and model everything and not to try and put everything in there to begin with. It's our role as engineers to understand the Pareto rule. What are the 80% of things that are important enough for me to look at and then expand the process? It could be good enough to start with something which is relatively small but sufficient to give me the view that I need, and then go and enlarge that as the system evolves, or as I have more resources to do so. I hope you enjoyed that. If there's any question, just shoot us an email And I really enjoyed having this session with you. Thank you.